Erica asked me this question before class, and as we were talking about it, two other students were discussing it. So I figured, hey, students haven't asked me to go over questions in a long time, which assumedly means the stuff's been easy for you. But I'll go ahead and work the problem just so it makes me feel like I'm earning my money, so to speak. So the problem, you're looking to purchase a small piece of land in Hong Kong. The price is only $60,000 per square meter. So, my house here in Lincoln is valued at, well, I bought it for $142,000. It was more than 2 square meters, I'll guarantee you. More than 3 even. So the land title says the dimensions are 20 by 30 meters. So I have length initial, let's say, is 30 meters. That's not a 30. And the width initial is 20 meters. By how much would the total price change in dollars if you measure the parcel with a steel tape measure on a day when the temperature was 21.5 degrees above 20 degrees Celsius? So we are going to measure it with steel that at 20 degrees Celsius has the correct length. So a few assumptions here. We're assuming that our measuring tape at 20 degrees Celsius measures exactly 20 by 30. But now it's hotter. If it's hotter, what does that do to the steel? It's going to expand. So when you measure with the steel 20 meters, you're actually measuring a little longer than 20 meters, which means you're getting a little extra land. So it's a little bit cheaper, right? So, you're going to save a few dollars. Well, let's see how much we really save. I said a few dollars. What is the concept going on here? Okay, thermal expansion. I put more words just so it would make more sense. The steel expands when you heat it. So the steel, I'm still going to be measuring what's measured as 20 meters on my tape, but it's going to be a little bit larger in reality. So we're going to determine how much larger it really is. So the actual length we're going to measure will be the original length plus the change in length. So the original length plus using the change in length equation, or more simply, so the length that we're going to measure compared to the actual length is given by that equation. And likewise for the width we're going to measure will be the original width times 1 plus alpha delta t. Now in the textbook, we had two equations here. We had delta L is equal to L naught alpha delta t, and delta V is equal to V naught beta delta t. But we had nothing to do with area. That's why I had to use the two length equations, because we had nothing for area. So we're going to make our area equation. Area is length times width. The original area is equal to original length times original width. Well, I'm just going to substitute what we've just calculated for length and width. So I'll have so that's going to be my new area. Well, we're all good at math in this class. I firmly believe that. And so we can all take this and multiply. Okay, everything has a L naught W naught. And then 1 plus alpha delta t times 1 plus alpha delta t is 1 times 1 plus 1 times alpha delta t plus alpha delta t times 1 plus alpha delta t multiplied by alpha delta t. So there's my total area. Now something that we physicists like to do. We like to get rid of small numbers when they're insignificant. Well, actually, I'll let you calculate this rather than just tell you we get rid of it. If we look at this, So somebody with the calculator, let me just randomly choose somebody. I see. Is that your calculator in your hand, Irving? Yes. Irving, go ahead and calculate what 2 alpha delta t is. Alpha is this value right here. And delta t is, for me, this value right here. So 2 times 1.2 times 10 to the minus 5th times 21.5. And somebody else with a calculator, okay, I'm going to ask Noah because I see she has her calculator. I really appreciate those of you who are following along with your calculators, by the way. Calculate what alpha delta t squared is. So just put 1.2 times 10 to the minus 5th times 21.5, and then after you have that, square the whole thing. So when you have your answer, let me know.
6.6564 times 10 to the negative 8.
How about you, Irving?
2.58 times 10 to the negative 4.
And I did 1. Mine was easy. I'll also do 20 times 30. I'm quick, right? So if we look at this, a physicist will normally say this number here is approximately 0. Why? Because it's so much smaller than the 2.58 times 10 to the minus 4. But then you might say, why don't you say the 2.58 times 10 to the minus 4 is approximately 0 compared to the 1? Is anybody wondering about that? The reason is we need to show some change. If we throw away this term, then we would have no change. And so the change is this, and this part is the significant part of the change. Now, just for grins, we can take 1 plus 2.58 times 10 to the minus 4 plus 6.6514 times 10 to the minus 8. We can put it all together. It's not going to change our answer from 1 plus 2.58. Delta area should be equal to area minus area initial. Come on. So there I dropped off the last term. Notice L naught W naught minus L naught W naught times, I put it in the wrong order. How many people noticed I put it in the wrong order? Should have been all of you. Should have all been clamoring to say, dude, you made a mistake. There we go. Okay, so this one will make those subtract out, and I'm left with delta A is equal to L naught W naught, which is 600 meters squared, times 2.58 times 10 to the minus 4, which, you still have that number on your calculator? Noah?
Oh, no.
Okay, well, it should be too hard.
6.654 times 10 to the negative 8.
600 times 2.58 times 10 to the minus 4?
The same number that you haven't calculated before?
I thought I had you do the 2. Oh, nope. I had Irving do it. My mistake. Irving, your 2.58 times 10 to the minus 4 times 600. I was like, that ain't close.
0.1548.
So the area that I will get with this steel tape is 0.1548 meters squared larger. Now that's a small amount of area, but at the price given, the difference in price is equal to our $60,000 per meter squared multiplied by 0.1548 meters squared. How much is that?
9,288.
How much?
9,288.
Now, of course, in terms of sig figs, we only had 2 sig figs. If you weren't doing it on the homework site, you'd put in 9,300. But since our homework site doesn't honor those, you put 9,288. Question?
What about the minus L naught?
That I subtracted those out. I had L naught omega naught times 1 minus L aught omega aught times 1 there. And so the 1 subtracted out with that. It's a very good question. So it shows that if you were buying this really expensive real estate, yeah, do it on a hot day. We'll have another example in just a moment that will further illustrate some of the interesting things that come with that. And that's the wrong presentation. This presentation. All right. I have to make a correction because I was talking to Ashley and she asked me about this and I was like, wait a minute, that's in the region. It gives you a problem, one of the reading quiz questions, that says you have a Reynolds number between 10 and a million. And I was like, well, between 10 and a million, that's our indeterminate range. And as the textbook explains, that's the range where the turbulence is growing on the backside of the object. Well, I reread the textbook and realized that my understanding had been flawed, and that's what I told you was flawed. This drag equation applies during the partially turbulent flow, not once it's reached that maximum number of a million. It's what's going on when you're between 10 and a million. So I said that wrong in class, hence my correction now. And so for that problem, because you're in the region between 10 and a million, then the force is proportional to the speed squared. And Amanda had that right. Was it you, Amanda? Oh, was it Etika? I don't know. Only one person had it in the homework besides Ashley, and she had it right. And then I was embarrassed because she had it right and I didn't. But now we've We've rectified that. Meanwhile, I'm wrecking other things. So I want to make sure I get that correction out there. Okay, temperature and heat. We talked about thermal expansion. My last demonstrations, last class period, were with a bimetallic strip. Something that has two dissimilar metals, two metals with different alphas. And so as the temperature changes, the lengths increase by different amounts. And the one that's longer is going to be on the outside of the curve. And you can actually calculate the radius of curvature based on the change in temperature, because if you have the thickness of those things, you have, okay, the change in radius is this big, and the change in circumference is 2 pi r. Okay, so you put in the same equation, you calculate what the radius is. We're not going to do that, but that's how a lot of thermometers work. The little thermometer, the traditional one that you stick in the oven, if you look in it, it just has this big coiled up spring thing. That spring is a very long example of a bimetallic strip. And so when the oven heats up, the length of the outer one grows just a little more than the length of the inner one, and it moves. Same thing for a garden thermometer. So you see those things in action, I'm sure. This here is a very simple way to measure your body temperature. You stick that thing on your forehead, and after a little bit, the nurse looks at it and says, your body temperature is blah, blah, blah. Anybody ever had this procedure? How does it work? Okay? You have that thing you put on there. It's in thermal contact with your forehead. If it's in thermal contact, that means heat can flow between the two. According to the second law of thermodynamics, what direction is the heat going to flow? From hotter temperature to colder temperature until you reach thermal equilibrium. What does thermal equilibrium mean? Okay, technically it means that the heat has stopped to flow. But if the heat stops flowing, that only occurs if they're the same temperature. So when you said same temperature, that's fine. I wouldn't sit there and mark you off on that technicality. So it's reached the same temperature. So when the polymer reaches the temperature of your body, they read it. Now that polymer is a thermal polymer. It's a polymer that actually changes color with temperature. If you've ever seen a mood ring, my son saw one for the first time last Sabbath, and he was like totally cool. Put it on. Oh, hey, look! I apparently right now am feeling, Those are the same thing. They're just thermal polymers. They change color with temperature, and so it's not telling you your mood. It's telling you your body temperature. So if you go play sports, your body temperature is naturally going to rise, and it's going to say your mood changed. And then this one here, this guy's checking the temperature of the air coming out of the vent. Kinda. What he's really doing is checking the temperature of the vent itself. Because the air coming out of the vent is going to be, if you're cooling, colder than the room. And so heat will flow from the metal into the air until the vent hopefully reaches the same temperature as the air coming out. And then it gives off radiation. We haven't talked about radiation, but it's waves coming out, like I talked about the waves from the sun that heat us. And so he's measuring those waves to determine the temperature. So those are different ways that we commonly measure temperature. The non-used temperature measurement for lab was set up. We have some sensors that we can do that with, so it was set up for those, but we didn't use them. Now, I talked about thermal expansion, so here's the expansion coefficients for different materials. Aluminum, brass, copper, gold. You see that aluminum expands a lot compared to, let's say, quartz. Quartz doesn't expand much at all. Now, we make our lab equipment generally, well, it used to be with Pyrex. Now there's another material. But notice Pyrex expands a lot less than ordinary glass, 1/3 as much. That's important. If I take ordinary glass and I have it at the temperature of ice water, now that's ice water, and I put the glass from ice water into my boiling water, what's going to happen to that glass? It's going to break. Why? Okay, the temperature change was too rapid. Too rapid. Because when the temperature changes, what's going to happen to the size of the glass? It expands. So you have the inside of the glass. Let's say the inside of the glass is where you put the hot water. I'm just putting more water in there. Nothing special about what I'm doing here. The inside of the glass expands and the outside stays the same for a few tenths of a second because it takes time for heat to go through the glass. Well, then you have a stress. A stress is a force divided by area in a solid. So nothing's going to break either. I'm just adding water. Everybody's watching like I did something interesting. So you have a stress because one part has expanded, the other hasn't. If that stress is too big, it breaks. So just recently, I made the mistake of taking a glass, a tumbler, out of the dishwasher, pouring cold milk in it, and it broke. Now, if it's a really thin glass, it's actually less likely to break. Why would that be? Okay, there were a lot of good answers. I couldn't hear many of them. I know that Gila was saying the right thing. You have less distance that the heat has to travel through, and so you're going to have less difference in lengths, less stress that builds up. But that's why things break, and we use Pyrex because it has a low coefficient of thermal expansion. What would be better to use than Pyrex? Okay, quartz would be better because quartz, the one I circled, has the lowest shown here. Well, quartz is it's a glass, but it's a crystallized glass. I can't remember what the material is they use now for labware. I think all of mine are still Pyrex because they're old. Yeah, I'm pretty sure Kymax is the name of the company that makes it, not the type of glass. Anyway, that's why they use Pyrex. That's why we like to use Pyrex in the kitchen. Small thermal expansion, less likely to break. I guess my last thing I showed you was was it bimetallic or was it the metal of the ball thing? I'm not sure which. But volume changes, and we had our example that we just did of area changing. Now I'm going to change from solid state to gas state. So this here is just a little pressure gauge with a bowl with gas in it. What kind of gas? Here's a hint. I opened up the valve to let air in. It just has air in there. So I'm going to take this and I'm going to put it in cold water. What do you think will happen when I put it in cold water? Okay, I heard trace all the way from the back. Pressure is going to go down. So it's at a shade over 15. Of course, I'm behind it, so I can't see. Is it changing? Move it. Yeah, it's now a shade over 14. So it's dropped by about 1. What are the units here? They're pounds per square inch. So it's down to about 14 pounds per square inch. Now I'm just going to let some gas out. So it should have gone up to somewhere around 15 again, right? You guys are so responsive. Yes, it did. Now I'm going to put it in my hot water, which is pretty close to boiling temperature. What do you expect to happen now? Okay, I heard people say go up. Is it going up? Thank you for answering this time. So it goes up, it'll keep going up for a while because it takes a while to reach equilibrium temperature. That is for the temperature of the gas inside to reach the same temperature as my water. Also, my water probably cooled down a little because I put something in here that was fairly cold. So the pressure went up about 4 pounds per square inch, which doesn't seem like much until you realize that's like 1/4 of an atmosphere or so. Right, so that's a pretty big increase in pressure. And yes, now she's starting to boil. Oh, wait, let's keep it in here, let it reach equilibrium. Down to about 15?
Yeah.
Put it back in the ice water. And it should come down to like 10 or so, right? So, that's a famous experiment in physics. If I let go, you know what will happen? It'll tip over and I'll have water everywhere. So I'm not going to do that. And so it's not going to stay there until it reaches equilibrium. So that's illustrating thermal expansion and contraction in a gas. Now, oh, I forgot. Speaking of gas, I wanted to show you this just because it's a really cool thing. You have a steel gasoline tank full of gas. So both the tank and the gasoline have a temperature of 15 degrees when you fill it up. How much gas is spilled when it warms up to 35 degrees Celsius? Why are you going to spill gas when the tank is filled up at 15 and then it warms up to 35? Is what? Okay, it expands. What is it? Okay, both the gas and the steel expand. To answer this correctly, you have to calculate how much the steel expands, how much the gasoline expands, and then the difference in those two will be how much spills. And so you have to go up to the coefficients of expansion. And so this table does not have gasoline. So I'm going to go with ethyl alcohol since the gasoline that I put in my car every day, I'm a cheapskate. It may not be the best choice, but I put in the gasoline that's 10% ethanol. It's cheaper, but the ethanol also carries less energy per gallon. Hence, the end result is it depends on what kind of car you have if you're saving money by putting that in or not. You could save money by putting in a higher grade gasoline. I have not ever done the calculation. So notice that number, 1100 times 10 to the minus 6 is the coefficient for volumetric expansion for something that's similar to gasoline. And if we compare that to steel, okay, this iron or steel, 35. The gasoline expands a lot more than the steel. You calculate the alpha delta T for one, the alpha delta T for the other, and then just like we did before, delta volume for the steel is equal to volume of the tank, alpha steel, delta T, delta volume for the gas is equal to volume of the tank, alpha gas, delta T. And the volume spilled is equal to delta volume gas minus delta volume steel. And does this actually happen? Yes. I have made the mistake of filling my car up on a cold winter day, parking at the garage, and then the next day it warms up to 60. And my garage smells like gasoline because, yes, it overflowed the stinking tank. Okay, water. Water is not normal. I've mentioned this. It's really important that water is not normal. Water is most dense, so this is a graph that shows density in units of kilograms per meter cubed on the vertical axis, and temperature in units of degrees Celsius in the horizontal axis. You can see this outer one shows the actual title. And so we're looking at the density of ice and water in this graph, and you see that the density is greatest there at about 4 degrees, 3.98, and then it drops down. When it freezes, the density really dives. So the water expands. And if you have that water constrained to be inside of a pipe, the pipe doesn't expand nearly as much as the water, and it bursts the pipe. So you break the pipe, that's bad. And if you continue to cool it, then what happens to the volume of the ice? Well, the density is going to increase, becomes more dense. That's more normal behavior. But you've got a long ways to go until you get up to the density of the water. So the ice floats. I've mentioned that's important. It's important because ice floats, forms an insulating barrier on the top of your lake. And so you can have water underneath that has not reached the temperature for freezing yet, and you have a water lake in the middle of the winter. So people can go out ice fishing. And I kid you not, every year there are people that will go out to Holmes Lake, drill a little hole in Holmes Lake, and drop a line down into Holmes Lake to pull up one of those mutant fish that must be growing in that polluted lake. I live by there. I smell that lake. It's not the perfect lake. I don't eat fish anyway, but I wouldn't eat anything that came out of that lake. It'd be like Blinky from The Simpsons. Okay, our first clicker question. What would happen to a lake in the winter if ice was more dense than water? The Trace exercise program, get on it. Irving's fighting it. Okay. Rebecca. That's it. So we had 1, 2, and 20. Almost everyone said the lakes would freeze over, and that is correct. Michaela, explain why that's the correct answer.
So I put that the lakes would freeze solid because they would freeze at the top as per normal, but then that would go down, so then it would just like.
Okay, that's the perfect explanation. You would freeze little flecks of ice on the top, and the little fleck, as soon as it freezes, sinks to the bottom. And so the bottom starts building up more and more ice, and you keep freezing the top because you don't have an insulator. And then you just freeze the whole darn thing. Hot air balloons. Anyone here been in a hot air balloon? Really? It surprises me. Not me. I'd be scared to death. I would leave the proverbial brown streak on the ground, I think. So how does a hot air balloon work? Hot air, that's a great start.
Air is less dense.
Okay, hot air is less dense. That is the key. Did you want to add to that, Erika?
Oh, I was going to say that one, but she has.
Okay. You have a burner, just a gas burner right here. And so that burner is burning air and gas. And when you burn that air and gas, it gets hot. Because it's hot, the gas is moving faster. I'm going to establish today why it's moving faster, because up to this point, you would have had to just take it on faith in your teacher. And I've told you not to believe what I say, to make sure that you're convinced and have reasons for yourself. So you have that hot air, it expands because it's hot. Because it expands, its density is lower than air. And so it goes into the balloon, you trap that hot air that's less dense. Outside you have more dense air. So if you calculate the weight of the entire balloon with its less dense air plus its payload, if that weight is less than the weight of the air displaced by the balloon, then you have a net upward buoyant force and it floats upward. Of course, ideally you get to a height where you're constant. In that case, you're going to have the weight of the displaced air equals the weight of the balloon. So they have flaps to control so they can let some air out and whatnot. And you don't want to get that air so hot and have so much air that you just go shooting up. Right? That's bad. You might have heard that tale, which I believe is a true tale, not just urban myth, of the genius who got his little lounge chair and put a bunch of helium balloons on it, grabbed himself a 6-pack of probably not root beer. The stories are very clear that it wasn't roots. And says, this ought to be fun. It would have only been better if he would have said to his friend, here, hold my beer. But so he had it tied off. He cuts off the cords, and he goes shooting up. Why would he go shooting up?
Because the balloon counteracted his weight.
His what?
The helium was a lot dense and they have a lot of balloons. They contracted his weight. And
Counteracted was the word. Okay. I thought she said contracted. I'm like, I'm not sure what she's explaining. Okay, counteracted. All of those balloons had helium, which is much less dense than air. And so the volume displaced weighed a lot more than the helium balloons, so that the total weight of displaced air was much bigger than the weight of him plus the balloons. Net force was, not just 0.1 newtons upward, it was a pretty big force, so he goes shooting up. And he keeps going. Now this guy was drunk, but he wasn't crazy, he had a BB gun. But he gets high enough and he realizes if I shoot those balloons, I've got a long ways to go down. Once I reach the point where I start going down, I might end up going super fast going down. And so he's up there, and at least the stories go, he's up like more than a mile elevation. Airplanes are coming into the LAX, and he's in their flight paths. And eventually he went out to sea, and they somehow rescued him. Great story. Using physics to full advantage. We're never going to try this on our own to see if it's possible, right? Maybe even if you did it with a dummy weight. And by dummy weight, you don't mean your friend that you don't think is very bright. Even if you do it with a dummy weight, if it works, you have a problem. Because there are airplanes and whatnot up there. And eventually a balloon's going to pop or something, and it's going to come down somewhere. And if you have a dummy weight, it's going to come down and hit something, and hopefully not a person. I think there's one, by the way, confirmed person who's been hit by a meteorite. That's bad luck. Okay, that has nothing to do with our class. Ideal gases. How many people have studied ideal gases in their life? Really? How many people have taken general chemistry? Really? Okay, I know you haven't, Eric, but the majority of the class hasn't taken general chemistry. I thought pretty much everyone except for Peter and Eric had taken general chemistry. Okay, so when you study ideal gases, my experience was the teacher just said, for an ideal gas, and didn't say what was ideal about an ideal gas. So I want to make sure it's clear what an ideal gas is. An ideal gas, just like our no air resistance trajectories for balls, just like our ideal pulleys that have no mass and no friction, our ideal strings that don't stretch and have no mass. An ideal gas is an idealized situation that is never perfectly occurring, although it's very, very close, indistinguishably close to occurring. So unlike all the things that I've done so far in physics, we do have lots of situations that behave very much like the ideal behavior. So what is ideal? Ideal behavior is if you have atoms and molecules that don't interact unless they have direct collisions. So that would mean they can't have charge, because if you have an electric charge, they'll interact at a distance. Second, when they hit each other, they have to have perfectly elastic collisions. They can't stick to each other at all. So that's condition number one for an ideal gas. They don't interact unless they directly collide, in which case they have perfectly elastic collisions. All the kinetic energy is returned. Second, the atoms and molecules have zero volume. Oh, sure, that exists, right? But if you think about it, in this classroom, even though we have, third to fourth root of a Google, of molecules in here. I never actually calculated what the third or fourth root of a googol is, but it should be somewhere around a fourth root of a googol molecules in this room. And that's a lot of molecules. You guys, how many people know what a googol is? Okay. A googol is 10 raised to the 100th power. And we have somewhere in the ballpark of 10 to the 25 molecules in the room. So that's why it'd be about the fourth root of a googol. Okay, that's a lot of molecules, but the size of a molecule is so minute that the space between molecules is still thousands of times the size of a molecule. And so because the space between them is so large compared to the size of the molecule, we can treat the molecules as if they have virtually no volume. So in this room, we are amazingly close to this idealized behavior of atoms and molecules have zero volume. Now the molecules are bouncing off each other all the time, and the idealized behavior there is they don't stick. Well, if you get close to the temperature where molecules are going to stick together, like the condensation temperature, then that definitely is not going to be elastic collisions. But if you have a kinetic energy that's way, way higher than the energy trying to hold them together when they hit each other, then you say, okay, that's a negligible percentage loss in energy, so it's almost perfectly elastic. And so if your temperature is much higher than the temperature of liquefaction, the temperature at which it would condense into a liquid, then that's ideal. Air, I don't know what temperature air becomes a liquid at, but I know it's really, really, really cold. So we're way above the temperature of liquefaction. So the room in this air, or the air in this room, is behaving very much like an ideal gas. So you can very accurately say the air in this classroom is an ideal gas. It's not a perfect ideal gas because that doesn't exist, but the ideal gas law is going to explain it perfectly. So let's look at the ideal gas law. It starts with Charles' law. I'm sure I'm pronouncing his name wrong because he was a French dude. But what he did was he kept the number of molecules and the pressure constant. So here, my pressure was changing. He has something like a balloon here, and it's just open to a big pressure reservoir, so it's going to stay at a constant pressure. And he puts it in something and sees how much the balloon expands or contracts, how much the volume changes. And what he found was that the volume is proportional to the temperature. What units do you suppose that temperature has to be in? In kelvins. Because it's the actual temperature, it has to be in kelvins. It's not the change in temperature, it's the actual temperature. So he found that the volume was proportional to the temperature. And in fact, no matter what the volume was, no matter what the gas was, if he took his data and extrapolated back to find at the temperature at which the volume would be zero, it all comes to the same temperature. And so that was the first inkling of an absolute zero. It was the same temperature for any ideal gas where the volume shrinks down to zero. So that's our first gas equation, Charles' law. Next we have Gay-Lussac's law. Gay-Lussac had the volume constant and the number of molecules constant. That's what I did. I did Gay-Lussac's experiment. Constant volume here because this metal isn't going to shrink or grow to any important amount compared to the gas. Put it in hot and cold, and he found that the pressure measured here is proportional to the temperature. So if our pressure went up by about 1/4 of an atmosphere, that means the temperature had to go up by about 1/4, again, what it was. Well, here it was 273 kelvins. Here, in theory, it's 373 kelvins. That's actually more than a fourth, closer to a third for the temperature increase there. So Gay-Lussac found that pressure is proportional to temperature if the number of molecules and the volume is constant. Finally, the last two experiments, Boyle did an experiment with, now I didn't re-look these up this year. I do remember, I think it was Gay-Lussac actually did most of these, but other people helped, and he only gets credit for one. Or it might have been Charles that did most of them. I'm not really concerned about that. We do want to give credit where credit's due. None of them are the Webb law for obvious reasons. So here, does anybody see my typo? No? Volume can't be proportional to 1 over volume. That would be ridiculous. Volume is proportional to 1 over pressure if you keep the number of molecules and the temperature constant. Or in other words, PV is equal to constant if N and T are constant. And finally, Avogadro's law. Avogadro looked at the volume compared to the number of molecules, keeping both the pressure and the temperature constant, and found that volume was proportional to the number of molecules. If you put all three of these laws together, you get PV is equal to some constant times NT. And so that constant is called the Boltzmann constant. I think it's 2 N's. So I think that's how you spell it. The Boltzmann constant. I have it written out in a later slide. So that is the ideal gas law. Is that the ideal gas law you're comfortable with? Okay, I got at least one yes. Some people said no. Why are you not comfortable with that? Okay, so it should be nRT. Okay, that N is a lowercase n. This N is a capital N. So we're going to see in just a moment that the two are the same thing. The microscopic form of the law, PV equals NKT. I changed the order of the K and the N. No big deal. Well, and there's the spelling of Boltzmann, so that's correct. The Boltzmann constant, obviously you'll be given it on your tests. This won't apply to the text next week. Yeah, there's my son. Hi, Nate. But it's just a constant. Avogadro defined a mole, a specific number of molecules, such that 1 mole of carbon-12 atoms has a mass of 12 grams. Right? That's what a mole is. And so if you calculate it, it turns out that a mole is 6.022 times 10 to the 23rd molecules. Hence the definition Na, Avogadro's number, 6.022 times 10 to the 23rd molecules. And unfortunately, Dr. Friedlein died 4 or so years ago. If you had taken chemistry from him, he would have come out one day with a little mole costume thing and really worked on driving home to you what a mole is. But it's just a number to help us calculate or work with big numbers of atoms easier. So capital N is the number of atoms or molecules. Na is Avogadro's number, this big number, and lowercase n is the number of moles. So when we talk about the number of atoms, we can say it's this many moles, or molecules, this many moles, or we can say it's this many total molecules. We'll get the same place. You just have to remember the relationship between a mole and molecule is the Avogadro's number. And so since N, capital N, the number of molecules is number of moles times Avogadro's number, we just substitute that in for the N right here. And we get PV equals the number of moles times NAK. Avogadro's number times K, we just give it a new constant, the, what do they call it? Ideal gas constant or something like that. And so the microscopic form of the ideal gas law is PV equals NKT. The macroscopic PV equals nRT. It sounds the same N when you say it out loud, but when you write it, capital N is number of molecules, lowercase n is number of moles. And so that's why they're the same relationship. It's very useful to remember then that NR, which is equal to capital N times K, is equal to the pressure times volume over temperature. In all of our physics experiments, we pretty much keep N constant. We can do that. we use what we call a closed system. We put a cap on it, so no gas goes in or out and N stays constant. Chemists don't have such luxury. They do things in open systems. They have a test tube that's open on the top. And so the number of molecules can move in and out. And so they do things a little differently because constraints, we in physics, we just say, we can always put a lid on it and use the closed system so we keep N constant, which means PV over T is going to remain constant. We're going to do lots of work with that. Okay, which condition is necessary for the ideal gas law to apply? Okay, Edika, you got to at least read it. Or were you reading ahead? Well, you answered the instant that it was available. Edward and Brittany. Just Brittany. Okay. 2, 4, 2, 15. Talk to your nearest neighbors. Discuss. Ask them if they read the slides, because this comes from reading, not from words that came out of my mouth. Okay, because our time will be up in 35 seconds, I'm reopening the poll now. Answer again. Oh, really? Forget it. It only let one person answer again. But that one person answered correctly. Second time around, we had 1, 0, 0, 0. The gas must be dilute. What were the two things I said for an ideal gas? They can't stick together. You have to have completely elastic collisions, and they can't interact unless they collide. Those were all combined in one. And the other one was no volume. And those two approximations give us what we call a dilute gas. And so that's why that was the answer. I didn't talk about the word dilute. Of course, I didn't intend to not talk about it, but I forgot to say that word. And so that's why it came in so low.